Okay, we're back looking at the week 4 group problem, and this is where things really start to get interesting because we're starting to get into motion in more than one dimension, where I think things start to become, you have to be a little more careful and know a little bit more, not just using logic that you're familiar with just from everyday common sense, but also using some more precise mathematical techniques, breaking things into components and so forth. So really hope that we get this understanding down. So let's look at the problem. It says, revisit the boat trying to cross the stream. The current is now 5 meters per second, and the river's width is 200 meters. We're revisiting in the sense that the worked example was also the same type of problem. So current is traveling at 5 meters per second to the right, 200 meter width of the river. The boat is traveling at 5 meters per second in still water, so if I label this as V of the boat with respect to the water, it has a magnitude of 5 meters per second, and it's traveling at an angle of 10 degrees downstream. Now, if you recall, there was a typo here. Actually, this was exactly the same as the worked example, so we're going to change things, and rather than it being 10 degrees downstream, we're going to say 10 degrees upstream, just to change things up. Okay? So, doing that, we're going to redraw the arrow just so we don't get confused here. This VBW, velocity of the boat with respect to water, is 5 meters per second, and it points 10 degrees. This angle here is 10 degrees. Okay? So far, so good. Okay, so it says, first of all, how long does it take for the boat to cross the river? Okay, well, in general, if you have this type of problem where the boat is setting its motion relative to the water and then the water itself is moving, what you're going to do is you're going to say that the velocity of the boat with respect to the ground, which is really what we most of the time care about because we're going to be stationary with respect to the ground ourselves, is equal to the velocity of the boat with respect to the water plus the velocity of the water with respect to the ground. Okay, that's the general formula, and note that this is a vector equation. That's really important. I have to add them as arrows in space, which might not point in the same direction, so angles and sines and cosines get involved. Now, this is all true, and I could process things from this point of view, but for this particular problem, I could also observe that in terms of the y direction, which is what matters for crossing the river, just getting to the other side and not caring about how far upstream or downstream I'm traveling as I do that, if I care about what we've labeled as the y direction, then this over here, the velocity of the water with respect to the ground, which is the 5 meters per second to the left, has no y component. It completely points in the x direction, which means that whether I'm talking about the boat with respect to the ground or the boat with respect to the water really doesn't matter. The point is that I just need the y component of this velocity vector. Now, if you look at the little triangle I just created, I'll label this as v of the boat with respect to the water. Again, it doesn't matter. It's the same as, for the y component, it's the same whether I'm talking about water or ground, but I'll label it as water. The velocity of the boat with respect to the water in the y direction, I can use this triangle to find it. And then you see that VBW in the y direction is equal to... The reason, by the way, that I'm finding this velocity is because I know the distance across the river. So if I find the component of the velocity that's taking me across the river, then to find the time it takes to cross, I can just divide it out. So anyway, VBW in the y direction from trigonometry here is the VBW times the cosine of 10 degrees. No, I'm sorry. My mistake. Sine. Opposite of that angle. Sine of 10 degrees, which is 5. VBW is 5 meters per second, so it's 5 sine of 10 degrees, which, if I grab my calculator, I'll take 5 times the sine of 10 degrees. Whoops, need to put that. Okay, so 0.86, 87 if I round correctly. So 0.87 meters per second represents the component of velocity that's going across the river, and then therefore the time to cross is just the 200 meters divided by 0.87 meters per second, which is equal to, again, just plugging that into my calculator real quick. Whoopsie, 200 divided by, the answer is 230. I'll just round it to that, 230 seconds. Okay? Very good. It's actually the same answer that we would have gotten if we hadn't flipped this across. You can see that the y component doesn't care if it's 10 degrees upstream or downstream, the way I've drawn it, which means this is actually the same answer as what you got in the worked example for week 4. Okay, now let's move on. The next part says, how far downstream does the boat land in the ground's reference frame? Okay, so now we really do need to pay close attention to this equation, because it says that we need to take, if we want the how far the boat travels in the ground's reference frame, we'll use the time that we just found, and we'll find a velocity that the boat has with respect to the ground, multiply velocity by time, and we'll get the distance. But now what we care about, since we're talking about how far downstream the boat goes, that's the x direction we're really referring to. So we're going to use this boxed equation, but the x component of that equation. So the velocity of the boat with respect to the ground in the x direction is equal to the velocity of the boat with respect to the water in the x direction plus the velocity of the water with respect to the ground in the x direction. Okay? The velocity of the water with respect to the ground, going back to our picture, is already completely in the x direction, and it's this 5 meters per second. If I take positive x to point to the right, then that is a positive contribution. So I'll put plus the 5 for that term, and then for the first term I'll look at my same triangle I had before, but now I want the other component. This is the VB water in the x direction, which is 5 cosine 10 degrees now, right? Just using same trigonometry as before. And now I have to be careful, because that component points to the left. See, this vector points to the left and up. So since left is negative direction, I really need a negative sign here in front of the 5 cosine 10. Okay? Don't leave that out. That's part of the component. Okay? So going down here again, this is negative 5 cosine 10 degrees. And figuring out what that's equal to, just using the calculator again. Negative 5 times the cosine, cosine of 10 plus 5. And again, I have to do that. 0.076 is the answer. Don't know if you can see that, but 0.076. Now that seems like a small answer, but it makes sense. I mean, 5, you're adding something to 5, and you're adding a negative 5 times cosine of 10. Well, cosine of 10 will be close to 1, since cosine of 0 is 1. So negative 5 cosine 10 is close to 5. So it makes sense that this is a small, and it's a positive number. So what does that tell us? It tells us that, in fact, yes, the boat does move downstream as it moves to the right in this drawing. If we had gotten a negative answer, which we could have, potentially, depending on if the current had been less, for instance, then we would be actually, the boat would travel upstream, because it's moving enough against the current to actually overcome the current completely, move upstream. But at any rate, now that we have this velocity in the x direction, the distance that we want, I'll even label it distance in the x direction just to be totally clear, is very simple to calculate. It's v boat with respect to the ground in the x direction times the time that it takes to cross, which we found both of those pieces. That's equal to 0.076 times from part A, 230 seconds, and this is equal to, once again getting the calculator out, 230 times 0.076 gives me 17.48 meters. So it doesn't go that far downstream. It's going 200 meters in the y direction, only 17 in the x, but that is what it is. So, all right, thank you very much for listening. We'll see you for week 5.